Both formal charge and oxidation states are ways of counting electrons, and they're both very useful concepts. Let's start with formal charge. So one definition for formal charge is the hypothetical charge that would result if all bonding electrons are shared equally. So let's go down to the dot structure on the left here, which is the dot structure for methanol, and let's assign a formal charge to carbon. We need to think about the bonding electrons, or the electrons in those bonds around carbon, and we know that each bond consists of 2 electrons. So the bond between oxygen and carbon consists of 2 electrons. So let me go ahead and draw in those 2 electrons. Same for the bond between carbon and hydrogen. Right? Each bond consists of 2 electrons, so I can go around and put in all of my bonding electrons. So if we want to assign a formal charge to carbon, we need to think about the number of valence electrons in the free atom, or the number of valence electrons that carbon is supposed to have. We already know that carbon is supposed to have 4 valence electrons. So I could put a 4 here, and from that 4, we're going to subtract the number of valence electrons in the bonded atom, or the number of valence electrons that carbon has around it in our drawing. And since we're doing formal charge, we need to think about all those bonding electrons being shared equally. So we think about a covalent bond. So if we have 2 electrons in one bond, and those 2 electrons are shared equally, we could split them up. We could give 1 electron to oxygen and 1 electron to carbon in that bond. We go over here to this carbon-hydrogen bond, and we could do the same thing. We have 2 electrons. We could split up those 2 electrons. We could give 1 to carbon and 1 to hydrogen. And we go all the way around, and we do the same thing over here, right? We split up those electrons, and the same thing here. So how many valence electrons do we see around carbon now? So let me go ahead and highlight them. There's 1, 2, 3, and 4. So that's the number of valence electrons around carbon in our drawing. So 4 minus 4 is equal to 0. So 0 is the formal charge of carbon. So let me go ahead and highlight that here. So in this molecule, the formal charge for carbon is 0. Now let's move on to oxidation states, right? So you could also call these oxidation numbers. So one definition for an oxidation state is the hypothetical charge that would result if all of those bonding electrons are assigned to the more electronegative atom in the bond. So let's go to the dot structure on the right of methanol, and let's assign an oxidation state to that carbon. We need to think about our bonding electrons again, so let's go ahead and put those in. Right? So we know that each bond consists of 2 electrons, so I'm putting in the 2 electrons in each bond. And let's think about the oxidation state of that carbon. Well, first, we need to know the number of valence electrons in the free atom. So just like before, we know that carbon is supposed to have 4 valence electrons. So this would be a 4. And from that, we subtract the number of valence electrons in the bonded atom, or the number of valence electrons that carbon actually has in the drawing. This time, we need to think about an ionic bond. So we're going to pretend like a covalent bond is an ionic bond, because we're going to assign all of the bonding electrons to the more electronegative atom. So there's no more sharing here. Winner takes all. The more electronegative atom is going to get all of the electrons. So let's think about the electronegativities of carbon versus oxygen. Right? We know that oxygen is more electronegative than carbon. So oxygen takes both of those electrons in that bond. So oxygen gets both of those electrons. Next, let's think about the electronegativities of carbon and hydrogen. We know that carbon is a little bit more electronegative than hydrogen. So for these 2 electrons, carbon's going to take both of them, since carbon is more electronegative than hydrogen. And the same thing for our other carbon-hydrogen bonds. Carbon is more electronegative than hydrogen, so carbon takes those. Carbon is more electronegative than hydrogen, so carbon takes those. And so how many electrons do we have around carbon now? Let's count them up. That's 1, 2, 3, 4, 5, and 6. So now we have 6 electrons around carbon. So 4 minus 6 gives us -2. So here, in this example, carbon has an oxidation state of -2. So there's no more sharing when you're doing oxidation states, right? Think about the more electronegative atom and assign both electrons to the more electronegative atom. Both formal charge and oxidation states are just really extreme methods of electron bookkeeping, right? They're not perfect. They're certainly not perfect, right? We're assuming that the electrons are either shared equally, perfectly, or that one atom takes both electrons. And neither of those concepts is perfect in the real world, but it works when we're drawing our dot structures and we're thinking about chemical reactions.